Goodness gracious gravy. Let's look at these steps. The first step is to draw a picture and label everything that's changing. Label that with a variable. That's what we did with the spherical balloon. We labeled the radius, the surface area, and the volume. Write down the rates that are given with derivative notation. That was the dv dt. Usually it's going to be with respect to t. Write down the rate that is required. That was the dr dt. And when it was required. We required the rate at which the radius was changing when the radius was 5. Now, if you blow up a balloon at a constant rate, you're giving it a constant volume, the bigger the balloon gets, the slower the rate at which the radius increases is. So if you had a really, really large balloon and you're pumping in, 1 cubic foot per minute, it's not going to change that much. But when you're starting out, when it's a really small sphere and you're blowing it up, the radius is changing really fast. So that rate is going to vary. So you need to write down when the rate is required. Step 4, write an equation to relate the variables that you're talking about. That's pretty simple. And then take the derivative of that equation so you can have the equation that relates the rates. That's the whole purpose of this. Plug in any values that you need or that you have to solve for what is required. If you need more values, return to the equation in number 4 and plug in stuff so that you can find more values to use. So with that said, that took a while to explain. Let's do another example. Okay, Leopold, good old Leopold, flies a kite at a height of 300 feet. The wind carrying the kite horizontally away at a rate. The wind is carrying the kite horizontally away at a rate of 25 feet per second. How fast must he let out the string when the kite is 500 feet away from him? Whoops. Alright, so on this one there's a couple different interpretations, but first I'm going to draw a picture. I have picture here. So there we go, we have a kite. Now, we know that this is 300 feet up. So we don't know how tall Leopold is, so I'm just going to assume this distance is negligent, but 300 feet up, that's how high this kite is flying. Now notice this is not changing because the kite is moving horizontally away. So since this is not changing, I don't have to label it with a variable. I can label it with the number 300 feet. And then it's moving away. So we can say that the kite is moving away at 25 feet per second. Yes. And that means this distance, I'm going to call that x. That distance is changing. Now also, the length of the string is changing. I'm going to call that s. So we have two things. I think those are the only things that are changing there. This is a right triangle. And also, okay, so there's 2 different ways to interpret this, and I'm going to interpret it in one of those ways. But I'll mention both of them. It says, how fast must he let out the string when the kite is 500 feet away from him? I'm assuming that the 500 feet is going to be the string length. Now, some people think, wait a minute, it could be saying that it's 500 feet horizontally away. But I'm just going to say that, well, it might have said horizontally away then. But the actual distance is the straight distance, which in my interpretation is going to be the length of the string. So we drew a picture with variables for the things that are changing. And then we need to write down the rates that are given. So it's important here to write down that x, because then we know that dx dt, we're writing down our rate, is 25 feet per second. Write down the rate that is required, the length of the string that we want to know how fast that's changing. So we want ds dt, when, and here's so write down the rate that is required and when it is required with derivative notation. Okay, so ds dt when I'm going to say s equals 500 feet. And then what's the next step? Write an equation that relates the variables. So how could I possibly, if I had a right triangle, how could I possibly relate those variables? Well, I can use Pythagorean theorem. And I know that would be 300 squared plus x squared has to equal s squared. That's just Pythagorean theorem. Now, I don't put in the 500 yet because s is a variable. I need to take the derivative first. So write an equation that relates to variables. We did that. Write the derivative of that equation that relates the rates at which things are changing. So if I take the derivative, this goes to 0. This becomes, I'm taking it with respect to t, so this would be dx dt, dx dt. Oh no, no, one. It would be 2x dx dt, right? 2x dx dt. You take the derivative like normal, tack on a dx dt. Same with this. This would be 2s ds dt. Now I'm looking for this rate. Yeah? So there we go. And what else? What else? I'm supposed to plug in stuff. Write down the derivative, take the derivative. Okay, plug in values and solve for what is required. So we got to plug in stuff. Well, I have s, so that I can plug in. That's 500. I have dx dt. That's 25. Oh, come on. I want to solve for ds dt, right? Yeah, that's what it says there. But I need x. I don't know what x is. And this is the part, this is what I was talking about. If you find that you need more variables to plug in, return to the equation that you wrote in step 4. So that was this equation. All right, so let's use this. 300 squared plus x squared equals 500 squared. Right, now I can solve for x. I got the 500 because of that. So the instant when s is 500, that will give me an x at that instant. So I'm going to solve. And of course, this is like a 3, 4, 5 triangle, except for it's a 300, 400, 500 triangle. That means x is going to be 400, or you could just solve. But there we go. Then I have that, 400. Then I'll plug everything in. I could divide by 2 and get rid of the 2's. So I guess I'll do that. And then I'll solve for ds dt. So plug everything in. Sweet. So 500 equal, okay. And then divide by 500, ds dt equals 20. And then I must have units. Well, this is feet per second. So Leopold has to let out the string at 20 feet per second. Okay, that's it. I'm done.